So, my topic is about optimizing with discrete decisions. If you want everything you do in this life, it's a question of discrete decisions. What is a discrete decision? Should I do this or not? Should I go there or not? Should I buy this or not? And did you study linear programming with Safia Kedad?
Yes.
There you don't have discrete decisions. You have amounts of something. How much should I buy? And this is a real number, okay? I buy 3.9 something, okay? What I want to tell you is that it is much more difficult to optimize with discrete decisions in the very large sense. For instance, take this problem that is easy to be understood even by somebody who does not work in computer science. You have 8 queens on this board. Please look at these queens that I placed here. What do you think about them? Do they attack each other? Take this queen. This queen, it can attack this. And this. And do the same for each other queen on this table.
And no queen will attack the other.
No queen will attack the other. So the question that I ask in discrete, it's a discrete problem. I ask to place on a chess board, you see, for n times n. This is the problem I ask. To place the queens, to place n queens that do not attack each other, okay? And this is a solution for n equals 8. Do you realize how this problem is difficult even for a human? Because let me think it this way. Let's take, imagine we had this. Imagine n is 4, and I take this part. How could you place 4 queens on this 4 times 4? Try to do it, please. You don't need to place this here, but imagine you place this queen here. Try to solve it in your mind, just to understand how difficult it is. It's difficult at the human scale, first, and then it will be difficult for any algorithm. What could you do? You can even come to here and place them if you want. You can come and tell me what should I do. Yes, I need 4 queens because n is 4 here. Think it this way.
One is white.
For instance, imagine we leave this here, and then we ask where should I need to place one here.
Yeah.
Imagine I put it here. I cannot put it here or here.
Yeah.
Then I get to this column. And here, on this column, it's not possible.
Yeah.
It's dead. So, putting one here goes to a dead end. This will lead to a dead end, okay? You follow me? I cannot put it here, not here, not here. Let me try here. The last choice.
Now we can add one.
I can add here 1. And now, not? No. So what will happen in such a case? We understand that this is not good. So you follow me? So I move it here if you want, okay? You follow me? Now what I do? No. Yes. No?
No.
Yes? No?
No.
Why? Ah, no. First it was okay.
Yeah.
Because this is no longer here,
Yeah.
sorry. Okay, cool. No. Yes.
So complete.
So we did it.
Yeah.
But do you realize that compared to linear programming where we have real quantities and you can play with some kind of region, feasible area of feasible solutions, you can move in the feasible area from one point to the other. You have many feasible points. Here, we jump all the time from one decision to another, and it's difficult to see how many solutions we can find. An algorithm for this can be even more naive than what we did before. A very naive solution would consist to do what? I have n columns, and how many choices do I have on each column? N. Column 1, I have n solutions. No, what we did before, when we go to the set reckoned column, we did not try everything, but the most naive algorithm will consider I have n possibilities for column 1, another n for column 2, another n for column 3, you follow me? I can place it, I have n choices here, and whatever I do here, I have another n choices here. This will lead to a naive solutions that will ask you to test n power n possibilities. This is crazy, okay? This is much too much. Even for n equals 4, a bit what we did before, 4 power 4 is this. It's huge. In computer science terms, this phenomenon is known under the term of combinatorial explosion. Combinatorial explosions, the number of possibilities is huge. Do you follow me? Think about it even in very simple terms. Whatever you plan to do today will be a sequence of decisions. Should I do this or not? And then should I do this or not? Should I do this or not? And I don't know if you realize, but the number of things you can do today depending on what you decide at each step can be huge actually. You see the metaphor a bit? Not really. You seem a bit lost.
What is an explosion?
Combinatorial explosion is when the number of possibilities you have is huge. Is when it's like playing it's like the number of possibilities you have when you do some betting, from sport betting. You see? Imagine you have to bet on 10 games. You have 10 games, and for each game you need to decide who is the winner. Let's say we have each game has a winner. Okay, football game, whatever. I mean, in football there is not always a winner, but give me a sport where we have a winner. Box. No? In box, one of the guys needs to win, and the other guy needs to lose. I don't know. Do you confirm? You cannot have a draw equal. Okay. And if you have 10 games and you need to do some betting for each game, how many possibilities there are? 10. No, pay attention.
20.
No, not 20, not 10. Each game you have 2 possibilities. Because if there are 20 or 30 possibilities, you would win. It would be enough to buy 20 tickets, and you would cover all possibilities, and you would gain.
This is 2 power 10.
This is 2 power 10, because for each game you have 2 possibilities. Once you decide for the first game, You have another 2, so it will go like this. I have 10 games. Let's say. Okay? This is the first game. I will bet on losing or winning.
Yeah.
I have two choices. Then I move to the second game. I can win or lose. I can win or lose. So here I have 2 choices. Then I have 4 points. I move to the next game, next layer, okay? Each one has 2 possibilities. Okay? So the total number of choices is 2 power n. Do you have any question, any remark? This is why you have this kind of... I don't know, I never bet anything, but...
That's why it's not easy to win.
That's not. It's very difficult to win in betting, in sport betting.
Yeah.
Okay? Because if you have n choices, generally speaking, and when I say n choices, you place a bet on n games, but the number of possibilities, the number of possible outcomes for the total number of n games is huge. Otherwise, you could win all the time quite easily. At least you could win 1 in 20 tries. But you basically never win. Actually, because why? Because the number of possibilities is huge, and you basically want to give one possibility. This is called combinatorial explosion, and it appears under different forms in all optimization questions with discrete variables. So let me show you how this will work for this queen problem.
What can we find?
Sorry?
I'm sorry. What can we find this PDF?
I will give it to you in the end, and I will put it on the website of Mrs. Kedad. And I'm recording the session today because you came later, but I will just recall the question I'm doing here. I have a board, n equals 8 here, but it can be a board of this size. I need to place a queen on each column so that what happens here, I do not have 2 queens that attack each other. This will attack this way, this way, this way, and this way. This is what I am to be. This is the solution I searched from the very beginning, but it's not the only solution. This is a problem in discrete decisions. I need to ask questions. Do I place a queen here or not? This is different from linear programming as we did it with Mrs. Kedat, where we speak about quantities. I don't know if you who arrived earlier understood the problem. No? So, I just want, this is not computer science, I want this to be crystal clear. I want at least when I begin my story, I want at least this to be clear. I ask you the following. I have this board, a very small one. Sorry for you who were here before, I will repeat this. This is a board. I want to place 4 queens on this board under the following constraint. I do not want to have 2 queens that attack each other. For instance, I cannot place a queen here and the queen here. They will attack each other. And I repeat, a queen is able to attack. If there is somewhere a queen, it's able to attack on the line, on the column, and on the 2 diagonals. Somebody who arrived a bit later, can somebody give me a solution for this? I mean, I can say this A, B, C, D. Where would you place 4 queens?
It can only take one step, or it can take more than one step?
More than one steps. All the steps.
Okay.
All the steps possible. No limitation. Only to stay inside the board.
Can you place on 4?
Only 4. I want 4.
Yes, but that's the way.
Yes, your colleague will help us.
I will try.
Try. Okay. Think about it as well. I think if we start this way, pay attention, because it's a good way. Here, if you do this,
Nasib 3D. No. Aku kata buruk. 3D. No, 3D. Problem. Aí não pode. Não, lá em cima. Só. Yeah. No.
Yes.
Yeah.
okay, try.
Yeah.
Now you see, it's not easy, because I could talk for hours to explain how difficult it is, but
Is it doable?
of course.
Yeah.
But the number of possibilities is so huge that it's difficult to find a solution, but it's doable.
4 is doable.
Nasib. Não sei.
No, because
Yeah. Hey.
if I put here,
Yes.
there's a collision.
Okay.
I think I can change.
No. This is it. The number of possibilities. You can do this, and then you change this, and you change this, and you go back and try again. But
Vai ter que mudar lá em cima. Vai ter que mudar lá. Nasib, mudei.
Can I?
Yeah.
of course, can you? Do you mind if your colleague can try to help you?
After the finish.
Okay.
No, Nasib.
There's no collision.
Yes, but you only have 3.
But yeah, I know Chinese. No. No.
Ești 3 timpul de acolo. 3
You had many decisions to take, but you know what decision was not good, in my opinion?
The corner?
The corner, the very first one.
Yeah.
Yes, this is my cheat code. If you place a queen there, it's not possible. You don't put a queen in a corner. This, if you start like this, maybe. Yeah. I don't know, but maybe.
I can try now.
3D, your colleague said, yes, 3D.
3D and 2.
3D
1C.
and 2A. And now that's it.
If I
Okay.
put in the corner, no possible. Okay. I get the idea.
This is called combinatorial explosions. You have many possibilities. There are countless possibilities.
No offense.
That was the
Yes.
that was the one. And what happens here at a small size, I will tell you now what happens at a very large size. Now let's see how a computer can do this. Now I have a short movie. I have
You can't count the number of solutions.
yes, the number of solutions. Actually, if you consider one solution per each column, in each column you need to place one queen. So for each column you can place n. You have n choices, n possibility for each column. what I was telling in the slide just before. This way, the simplest solution, but I will tell you how can this be improved. If you want to test all solutions, you have n power n, because for each column you have n possibilities and you have n columns. But of course, computer scientists studied a way to reduce the number of solutions. This is the main question: how to reduce the number of solutions in discrete optimization. We want to minimize the number of possible solutions. Let me now, I will show you, this is a solution computed by the computer. For each line, it tries to place the queen. A bit similar to what we did before. He started with a queen in this corner, exactly like your colleague. And now he tries to build the solution. The number of possibilities, maybe it will not be n power n, but very, very huge still. And you will see how huge it is. Because it gets here, and now it's dead. This means this is not possible, and it goes back and changes this. You see how it works. It managed to place it here, okay? It's enough to watch the video. No words are necessary. No? This is not good. It goes back. It went back to this one. If you had to solve the problem, we could try something like this, and a computer could do the same. Okay. We are almost done. Yet still almost done, but we are far from exploring everything, and maybe, unfortunately, at the very last moment, actually is nothing. Do we need to go back? And now, we need to go back again. Okay, so you realize. Now we realize the most important. We realize what is the most important question when doing this. What's the question? Is it doable?
In the way he is trying it, maybe he will stay forever?
This is the question.
Yeah.
Will this take forever? If we do this is the question. How long until we find a solution?
The maximum is
Infinite.
And wait, for me, n power n, something like that, if it's exponential, it's infinity.
Yeah.
In some sense, in practical sense, it's infinity.
Yeah.
So the big question, if I leave this continue like this, okay, it will not take forever, you realize me, but I can go home and come back at the end of this course and say I did my job, because will it finish today? How long do you think it will take? You realize it can take a long, long time. After your intuitions, however, it's not a scientific question. This is a video I downloaded from the internet, actually. I have a finite amount of memory here, so this video will end. How long do you think it will take? 1 hour, 2 hours, 3 days? I don't know.
Maybe one day.
Maybe one day.
Remove the first one, I think.
Maybe until we move this one. Maybe. Maybe not. Because there are so many possibilities that it's very, very difficult to anticipate. in that when n is 4, I knew, because I knew it for n4 you have to not place a queen here. But when n is bigger than 4, I don't know, because there are so many configurations that I cannot find, let's say, mathematically a proof to show you have to put. But okay, research that is done in this area works with this kind of arguments, because maybe it will finish now, whenever. Who knows? No. Okay.
Maybe it will take 1 week.
Maybe it will take 1 week. But you're real. Okay, my point is to make you understand that when you have this kind of discrete decisions, it can take forever, because it's a combinatorial explosion. The number of configurations, it's a combinatorial. It's huge. Okay, if you really want to know, this will end today in no more than half an hour.
That's not too much.
Not so much. So we are at 5 minutes and 30 seconds. Okay, 24 minutes and it's finished.
But the computer is working faster than that.
Okay, that's the point. The computer is working faster than that, but as n gets bigger, the number of combination is increasing in an exponential manner. Okay? We never have enough resources for this problem if we solve it this way. Of course, we can do it for 8, but if instead of 8 I say 100, it's dead even for the fastest computer we'll ever have. Okay, so if you want, let me go forward. Minute 12, 15, 16. Okay. Minute 26, 26, 27. Okay, now I think maybe here it's up to finishing. I still have around 1 minute and 20 seconds. Oh, you already see that queen in the top left corner is good in this case, because it will finish. Really, I still have 1 minute and 7 seconds. So, you understand the story. And this is, I don't know. Oh no. No. I don't know how it will finish in 30 seconds, I don't know. No, sorry, maybe it was a mistake somewhere. I see. Okay, now this works. Okay, did you see the solution? It should finish in 17 seconds. That's it. Okay, that's it. Okay, 7 seconds. Finally. Okay. The number of possibilities is huge, and all problems in discrete decisions will end up facing this kind of huge number of possibilities, combinatorial explosions. Let's take a look at a slightly faster video of the same story. Okay, now I can make it faster, but it's column-wise the same story. Okay, now, okay, as we said, okay, now it's faster, okay? I only have to wait 48 seconds. Okay, and it's faster, okay? On the computer, of course, will go even faster if we try to do this with an algorithm that displays nothing. Okay, I think. Okay, faster speed. But you see, now you see very rapidly how many solutions there are, okay? Okay, I don't know if I think it's the same solutions but turned rotated. Okay, and I will discuss with you how this phenomenon can appear in any kind of problems with discrete decisions. Let's say I have this problem, which is not a computer science problem. It's a game I will call a Monopoly. What happens? I start at Go. What can I do? At any moment, so I move left. This is money. If I get here, I gain $5. If I get here, I lose $21. What can I do at each step? I can jump 2 positions. I can jump 3 positions. And I can say bye-bye. I leave with the money I have up to now, and I stop playing. Okay? The goal we imagine is to take the maximum amount of dollars we have from this game. Okay? It's not about lucky strikes. It's about thinking, what should we do to get the maximum amount of money? You understand the game?
The maximum is to gain everything and lose nothing.
Yes, if possible. Only that.
I think
But do we have to follow that instruction, or we can just do anything?
You have to do one of these 3 things.
Okay.
So,
I mean we can jump like 3 position 3 times.
yes, this is a possible solution. One of the possibilities is to jump 3,
And then 3.
and then 3,
And then 3.
and then 3. If you do this,
Yeah.
you will gain
$14.
$14.
Yeah.
3, 2, 2, 2.
Another solution is to do 3 to 2. Your colleagues. This. And this way you have 16. Yes,
Oh yeah.
it's better.
Yeah.
But you understand that the number of possibilities is huge, because even if the second solution is better, maybe we can do even better. How can we prove this is optimal? Because up to now, what you gave me is what we call, do you know how we call these things? We call them heuristics. You gave me a possible solution, a heuristic. But I have no way to prove it is optimal. I have a solution which may be good enough, but you understand me. If these numbers are billions of dollars, we want to be optimal. Okay, if it's fingers, I don't know, maybe we don't want to be optimal, but generally speaking, in this course, I want to be optimal, because otherwise... Okay, so let me show you a bit in the style of the previous queen problem, how we can solve this problem. And you'll understand how difficult it is to consider discrete decisions in everything we do. So I have this. How will this problem work? I start from here, a bit like for the queen problem. I have the first decision. The first decision for the queen problem was where should I place the first queen on the first column. What can I do? Let me, if you want, I start from here. No, I don't know. Okay. You understand. The starting point is there. I will play this way. I will consider this way. If I go up, I move, it's a jump of 2. If I go down, it's a jump of 3. Okay? If I go up, what happens here? minus 21. I have minus 21. If I go down, I have 15. And don't forget, at each moment I can leave the game and say bye bye. Okay? Minus 21 I jump this way, 15 I jump this way. Okay? Yes, okay. Okay. How will the algorithm work? I have this, and let me write here what I call, it's a maximization problem. I want to maximize the profit. Let me write here what I can call the best lower bound. What's the lower bound? I maximize something. A lower bound.
Is the minimum?
Yes, I have a lower bound. It's less than equal than the optimum value, which is less than equal an upper bound. Okay?
What is exactly the lower and upper bound?
The upper bound, I don't know it up to now. But I will discuss this with you, because I will play with lower bounds and upper bounds. What can I say for the moment is that I have a general lower bound of 15. Because basically if I jump here and then say bye bye, I can go home with $15. Okay?
This is the upper bound?
This is the lower bound, because what does it mean? I want to maximize the profit. I show you I can gain at least $15. So this is a lower bound, because I gain at least 15, but potentially I could gain more, which means the optimum, okay, a lower bound less than equal than the optimum value. Okay. But now you already see something. Do you remember the two solutions you gave me in the very beginning? One had a value of 14, if I remember correctly, and the second one of 16. Okay, this is the lower bound, which tells me from the very beginning that I should not bother with the solution of value 14, because the optimum value cannot be 14. The optimum value is at least this or bigger. The optimum value is but now I can compute an upper bound. Now because you will see later why do I need upper bounds. If I don't do upper bounds, what will happen? For each decision I have two choices. If I have n decisions, total number of choices will be
N times N.
no, 2 times
N
n.
power.
2 power n, exponential. It's crazy, it's not possible to work with 2 power n. But now I will play with upper bounds in the following sense. Let me first give you a general upper bound. A general upper bound, do you know what can be an upper bound for this problem? When the game starts, I can find an upper bound for the game. You know what can be the upper bound? No, this is a lower bound. The upper bound, I want to say something. From the very beginning I say, I write it here. I have 15. Sorry. Don't make these confusions between the bounds. I have 15 less than optimum value less than something. What can I put here? The general optimum value. From the very beginning, can you give me an example of an upper bound? 32 maybe. What is 32?
Without losing anything.
Yes. I take all positive values on the table. In my dreams, if I could cheat, what could I do? I could take this and this 20, this 32. So from the very beginning of this step, I know we can have other upper bounds, but from the very beginning, you know the upper bound, the optimum value is between these two values. Okay?
And then update.
Pardon? Sorry?
And then update the
and then we will update this. We will build a tree of decision. We will call it branching tree or decision trees, and we will know what will happen. But already,
Sorry, can I ask a question?
of course.
I don't understand why we got this thing. And the minimum we can get is minus 21 or...
Yes, the minimum you could gain is minus 21.
Yeah.
But this means that this is true. I can say minus 21 is less than equal than this. Okay, this is true. But I can also say that if I do this, I mean if I make a jump of 3 and then go home, I can have, this tells me that the optimum value, no, this is also true.
Yeah.
This is true, and I don't know if you jump this and go home, you may find that you also have 7 less than the optimum value. Okay? All these are lower bound for my problem, but what we want is the best lower bound. Okay, so what we will do as we explore the branching tree, we will squeeze the lower and the upper bound to make it closer and closer.
Yeah.
Okay. Okay, now things will get a bit more difficult because here I call this a branch. I go here and this is a branch. But once this decision is taken, if I go here, I'm no longer on the original problem. Now I am here. I am on this branch. And now I can analyze the problem on this branch. What can happen on this branch? I will write it this way. Minus 21. I can go home on minus 21. So, I can say...
I jump 2 or 3.
Yes, I will soon go to this, but I want to write something like this, but related to this branch. I can say that on this branch, minus 21 is less than equal than the optimum value on this branch. And now let me find an upper bound on this branch. What would be an upper bound on this branch? I don't know, did you want to say something related to this?
Maybe I can jump 2 or 3 from this position.
Yes.
That's what
For instance, we could jump 2 or 3, and this will give me, if I jump 2, 3, 2, it will give me something. But even in my wildest dream, even if I imagine I could gain, I can take all the money that I still have in front of me. Imagine, I'm here, but I'm in my wildest dream. Even if I could cheat a bit, and if I take all positive values that are still behind me, this will get me to minus 21 plus
minus 32 minus 21.
Okay. So the positive values on the game, it's an amount of 32, and minus 21 will give me 11. Which tells me that on this branch, the optimum value in this branch is between this lower and upper bound. What can I say from this moment on?
This is not a solution.
So I cannot find a solution to my problem on this branch because, generally speaking, I have a general lower bound of 15. I know I can gain at least $15 from this game, and if I stay on this branch, I cannot make more than 11. So from this point on, I will not explore this branch as crazy. It's useless. This is called the pruning. The branch is, this is the technical term if you want. The branch is pruned. which is quite natural if you want to look at the problem. What do I mean by that in very down to earth terms for a non-computer scientist? I tell him, my friend, look, you start here, you go here and you take $15 and go home. But my friend, if you go here, you already lose 21. Look around a bit. It's better to take in the worst case, you take the $15 and go home. Because if you start with minus 21, look, there is not enough dollars here to compensate this initial loss. Okay? It boils down to this.
It's the two, but because we can count them.
Yes.
If we cannot count them,
it will be more difficult. It will be much more difficult if we had 1,000 positions to go. Because maybe you lose in the beginning, but you gain something bigger later. But up to now, okay, to understand the story, we have this. So, basically, I'm here. So here, this is less than equal than the optimum value. And here, if I take all the values, positive values that remain, on this branch I'm here, okay? Okay, so now I'm here. Okay, what can I do now? I can, sorry?
Sorry, can we consider in the first case that we cannot count them and we continue as if we can gain more? We can take two possibilities, 2 and 3.
Yes, if we did that, I would continue branching here. But if I did that,
but because we previously know that it's not possible.
It's not. It does not pay off. It's not. It is possible, but
it's not the maximum.
It's not the maximum profit is not there.
So this 21 is annihilated for our.
Yes, it's cancelled. Is forgotten. The technical term is pruned. No. Okay. Pruned. Okay. So we can focus on this, and then I can go up. And if I go up, I move 2. I go to -8, that is. So, what happens if I go up? I will have here 15 minus 8, 7. So less than the optimum value on this branch, which will be less than, I moved here. What can happen in my wildest dreams, even if I could cheat, I could gain all positive values that are still behind me, which is 12, which will give me an upper bound of 12 plus 7, 19. On this branch, I move 3. I will end up 15 minus 7, you follow me, 8. Less than the optimum value here. Okay, less than, I'm here, and I gain the 12 that remain. 20. Okay. I cannot cancel any of these branches, because the optimum value, it can be either here or either here. But if you want, it could be quite interesting to do now. Look, I have these are called open branches. I have 2 open branches. This has an upper bound of 19. This has an upper bound of 20. Actually, what I can think about it, what I can say now, here when I first started, I had an upper bound of 32. I have these two choices, which tells me that the upper bound, the general upper bound, actually now can be reduced to 20. We cannot be worse than 20, considering these two bounds. So now already from this step,
Why not 19?
because maybe the optimal solution is here. Maybe the optimal solution is here because but the main point, even if you took 19, you reduced the bounds. This is the gap. When we first started, we had a gap 15, 20, 32. We reduced this gap 15, 32 to something like 15, 12, to 15, 20. So we already have some closer bounds, tighter bounds of the optimum value. So I could say to somebody, my friend, even if you take the $15, okay, in the worst case you lose $5. So if you don't have enough time, go home with your 15s and be happy because you didn't lose so much. I have some information on the optimum value. I try to find a tighter gap. So now let me explore this. I have this 719. Where am I? I'm here. That's it. If I go through, I move here, and will get me a lower bound of 10, which is less than optimum value. You follow me? Less than. What do I have behind me? 9.
Yeah, 9.
So I am on 19. Or I could jump 3, and I'm here, which will give me another 10. But the upper bound will be what remains behind me, 16. Okay. I have to keep this open. I will get a bit faster now. Here, this branch, it supposes I'm here, okay? If I go behind me with 2, I will gain 3 points, so I'm at 11, less than optimum value. And I still have 6 behind me, that's it. From this point on I can, if I'm here, because this boils down to, no, I can update a bit my algorithm for computing the upper bound. If I'm here, what does it mean? It's finished. The game is finished because it's clear. I have to leave because I cannot take this one. It's clear. So I can be a bit smarter when I compute the bounds. And I will say less than 11. Why? Because I'm a bit smarter here when computing the bounds. This will enable me to destroy this branch. Okay? On the other branch here, instead of because recall, moving up, we move 2. Moving down, we move 3. So if we go down from here, we get here, and here I no longer have to compute a lower and an upper bound, because this is the end of the game. If I'm here, and this I will have, optimum here is 8 plus 6, 14. This is one of the solutions I was given in the very beginning. The optimum value is 14 on here, I'm here. Game is finished, okay? So I'll cut it. Okay? Maybe you are a bit lost because you no longer know where I am. But I will try to remember. This one is jump of 3, jump of 2, jump of 2. This is I'm here. Okay, and from here I can only make a jump of 2. If I make a jump of 2 from here, I have optimum value 16. The other branch was, look, what is this branch? Jump of 3, jump of 2, jump of 3. So it was jump of 3, jump of 2, jump of 3, that's it? Okay. But basically, do you follow me? This is?
I think the optimal is 10.
Basically here I need to go home. Yeah. If I'm here.
Yeah, there's no more.
No more jump. Here actually I should have said from the very beginning the optimum here is 10. Okay, so now I don't care about this anymore. And this is the final solution. You understand? This branching tree gets bigger and bigger and bigger when we add more and more positions. You understand me? Okay, so this is what I will call later the branching tree. You will also find it very often if you will ever study artificial intelligence, where we have in many artificial intelligence branches, you will have this kind of decision trees. Do you know the algorithm for playing Go? The algorithm for the best algorithm for playing Go, the one who managed to beat everybody, best Go algorithm. I don't know how to place. Sorry, my internet connection is not good. I can. My internet is not good enough. This is Monte Carlo tree search. The strongest algorithm for playing the game of Go is Monte Carlo tree search. If you want, Monte Carlo tree search for Go. I don't know. English Monte Carlo tree search. I don't know if you see it clear, sorry. This is the rating of the best Go playing programs. Since 2006, which is around here, all of them use Monte Carlo tree search to play this game against a human opponent. And this Monte Carlo tree search, just for your information, is something a bit similar to what we did. It's about exploring trees like that. sorry, the quality of the projector is not good enough to make you really see anything. But you start from some point, you have some choices, and then all I want to say, you end up by exploring a tree of possibilities. But here, since you have an opponent, some of the layers represent your moves, some other layers can represent the moves of the opponent. But you'll still end up with a huge tree, and the great difficulty is to explore this tree in the most intelligent manner, so as to guide, to limit the number of branches you explore to the most interesting ones. So there is, generally speaking, a huge family of algorithms in optimization of artificial intelligence that basically work with what we call tree search, okay? This is Monte Carlo tree search. It works for some problems, but there are other search algorithms, okay, that explore trees a bit like what you have seen with me right away, okay? You can use it for many other board games, okay? This is for your information, I understand, okay? Okay, now I will move to the optimization part, because it's a course on optimization, on operations research. Let me ask you an interesting problem for me, but I'm not sure it's very pedagogical, let's say. Imagine a guy gets into a bank, breaks into a bank. Imagine he can steal some things from the bank. He can steal either gold bars, he dreams about them, and he can also steal bill packs. But, of course, you understand me, even for the bad guys, even them do have some constraints. Because I suppose he cannot take everything inside the bank. He does not have enough time. I have two constraints. The guy only has a knapsack, and the knapsack is not able to take more than 20 kilograms. Otherwise, I don't know. I suppose the bad guy is not so strong. He cannot carry more than 20. I don't know. If this is possible, what? I don't know. Everybody cannot carry more than 20 kilo. Maybe he's just a very smart guy and he managed to break the door, but he's not so strong. And anyway, a knapsack has some limit of capacity, any knapsack. This is the volume. Okay. Imagine he cannot, the knapsack cannot allow more than 32 liters. He cannot squeeze more than that. Okay, so this is the problem the guy has to solve. Each gold bar will give him a profit of, I will say $3 if you want, but you understand me. It's not $3. A gold bar can be $3,000. Okay, but $1,000. Here the objective values is in thousands of dollars. You need to pay attention. Okay, a bill pack will give you 1 unit of profit, $1,000. The gold bar has 8 kilo, the bill pack 3, and both of them have the same volume. Okay, the same size, 6 liters. Question: the guy, if the guy has only, there was a song, all I have is 4 seconds. If the guy all he has is 4 seconds because the police is on the way, imagine what would you do in 4 seconds?
2 gold bar and 1 bill pack.
Okay, and go home. Okay. This will give you a profit of 7. Okay, you did all the calculations. Okay, so weight, in terms of weight, you will use 2 times 8, 16 plus 3, okay? And in terms of volume, basically you multiply the number of items, which is 3, by 6. because both of them have the same. So you have 3 times 6. Okay, and you go home. This is a bit what happens in computer science as well. You use a heuristic if you do not have enough time. Okay, you do, for instance, you do a Google search. You know the engine behind. He knows, the guys at Google knows that the user is not ready to wait 1 minute to get the best answer or whatever. The Google has to give you the reply in 1 millisecond or something like that. So in this case, basically the result will be more or less of a heuristic. In computer science and optimization as well, if we don't have enough time, we need to use a heuristic as well. If the guy has 1 minute to think about it, since the objective value is in thousands of dollars, it could be interesting, however, to know if he can think about it 1 minute more and he gains $1,000 more. It's one of the most profitable minutes of his life. If 1 minute of thinking on $1,000, this is something. If I think with you now for 1 minute, I will not get $1,000. Neither will you. Okay, what do you think? Is there any hope to do better? I wait 1 minute.
You can sort out some functions.
Sorry?
Sort out functions like we know our limits and we know the price for the golden bars and the price for the bill. And I don't know. Look like the one we did before.
A bit.
No, I mean.
What is the question again?
I give you 1 minute more.
Okay.
I know you told me just before that how you could go home with an objective value of $7,000. Can we prove this 7 is optimal? And if it is not optimal, is there any solution with an objective value of 8? If you go from 7 to 8 for this problem, this means $1,000 more. It's not exactly like the previous problems, but I will get back to it soon. Just think about it and give me any idea. No.
Only takes cash.
Think about it. We could take the maximum amount of cash. What is interesting here? You cannot take 3 bars because each bar 8 kilo. 3 times 8 is 24, and you cannot go. The capacity of the knapsack is 20 kilo. You cannot take home more than 20 kilograms. Okay. But think about it. Think about this. Take more money than gold.
I think the one gold bar 600 4
What do you think about this? 1 gold bar
and the
4 4 bills.
yeah.
You will also get 7. And this is a second optimal solution. Take 1 gold and 4 bills. It's a second optimal solution that is feasible. And this is also an interesting phenomenon. in optimization, because when you have two optimal solutions, do you know why this is interesting? Because what happens very, very often in real life, the parameters that you have, they are some approximation of the reality. Because I can consider that one bill has this amount of dollars, okay, but the price of the gold bar can go up and down tomorrow, and it's an approximation. Because if the price of the gold bar is not this, but 2.9, if the real price of the gold bar is 2.9, actually the second solution, which takes only one gold bar, it's better. You'll become better. Yeah, you change a bit the objective function actually. And, but on the other hand, if the price of the gold goes up, the first solution is better. Okay. Another interesting thing to study is, and this is why it's important to think of multiple solutions. What if the guy could make the effort to carry 1 kilogram more? It may pay off, however, a small effort to, you understand me? Let's say 20 becomes 21. A small effort once in your lifetime.
It's
not big deal. No?
Yeah.
But will this change anything?
You can carry 3 golden bars.
No. 3 golden bars means 24 kilo.
2 gold bars and
2 gold bars.
7 pairs. Still 7.
2 gold, I'll write 2 gold. Can I take 2 gold and 2 bills?
No.
No. No.
More than 2 golden.
No. And if we think about the other solution, which was 1 gold and 4 bills, can we move from this one to 1 gold and 5 bills? No, because here you have 6 items. Each item has 6 volume. We need 36. So I cannot do this. And from this one, what I said before, I cannot move to the. But now I try. So I try to squeeze something more in the knapsack. This does not work because it will ask for a volume of 36. And I imagine that the knapsack cannot, however, extend in volume. But this solution, however, will respect the volume constraint without problems, because it will need a volume of 6 times 4, 24. But the problem with this one is the weight. 6 gold plus 2 bills will ask for a weight of 2 times 18 plus 3 times 3, 20, 22. So the answer is, if the guy is ready to make the effort to carry 2 kilograms more, this effort will give him $1,000 more. Okay, so I let you think about it, but you already have the intuition that for the given constraints, he cannot gain more than 7. For this constraint, you already have the intuition, you cannot carry more than 7. But now I want to prove it. I will prove it soon. But now let me write the official, let's say the formal model for this kind of problems. I will write it this way. Maybe you already studied this kind of models with Satya Kedad, no?
Yes.
What do I have here? X1 is the gold, I recall. X2 is the bills. I maximize this, maximize the profit. I have the weight and volume constraint. I suppose it's okay now. You studied similar things. What is different compared to what you did with Satya Kedad is this small thing. These variables are integer. From this point on, the problem becomes much more difficult in computer science terms. Linear programming, where you have real numbers here. If you have real numbers here, it's linear programming which can be solved in polynomial time, and it can be solved very, very rapidly using Julia or something. This is not polynomial time. This is NP-hard. The problem is NP-hard. Okay? And today you will also have in the second half of the lecture of computer class for solving these kind of things in Julia. Because Mrs. Satya Kedad told me that she explained you how to install Julia. Before going to the code,
Only send us PDF.
Sorry?
Only send us the PDF.
Of course, I will send you right away. But now,
No, I'm talking about the Julius. We didn't download it. We downloaded it at home.
you didn't do it?
We did it at home.
Okay, it's perfect. But now, let me go back to the question. I have this, and I want to know, okay, I discussed with you two solutions with value 7. The question is still not solved. I still did not solve this to optimality. What means solving this to optimality? I don't know if this value of 7 is optimal or not. Do you understand me? Or would you prefer to take a short break, think about it later? A short break, and if you think of during the break, if you can prove it to me, that 7 is optimal. Whatever means necessary, you can think about it. But we can do it. No, it's the half point of the session. We do a 15 minutes break. That's it. This is what you do, and you tell me after if you can gain 8. Please, for $100,000, can we find a solution of objective value 8? Or this give me your intuition? What do you feel? Is it possible? I think you did try multiple solutions. I think you covered the best solution already. I don't think it's possible to go home with $100,000, but I will tell you why, and I will give you first the explanation without using a computer science terminology. The guy is here. He has 1 minute. He has this problem. I don't speak in terms of computer science, but this will translate, it will boil down to the notion of linear relaxation. The guy can ask himself the following question. Okay, what happens if even in my wildest dreams I can imagine I can melt the gold? Imagine I could have the tools, the technology to melt the gold and to cut the bills and to take fractional amounts of gold and bills, real numbers. Imagine in my wildest dream I may want to go home and I can take 2.5 bars. What is the optimal solution of the problem in real numbers? Okay. In my wildest dream I can melt the gold. Now think about it. What is the optimal solution? You can melt the gold. You know what you can think about?
Take a half.
Take
2.5.
2.5 gold bars.
Yeah.
Basically, you take the maximum amount of gold possible. But do you know why you do this? It's a good answer, but why did you choose it this way? Can you try to?
Because
Why?
in terms of weight,
Yes?
so the gold is more worth to take.
Yes. So, yes.
The
Because
price of gold is more.
Yeah.
yes.
1 kilogram of gold
Yes.
is
Yes. 1 kilo of gold is worth more than 1 kilo of bills. And 1 liter of gold is worth more than 1 liter of bills. Basically, it's a kind of value per unit. The value per unit for both units, volume units and weight units, the price per unit of gold is bigger. So in this case, it's always more interesting to take per unit more gold than bills to give you more. So in this case, yes, in this case, we say that the optimal solution in fractional number consists of taking the maximum possible amount of gold, which is 2.5 gold. And now the question is, okay, I take two gold bars and a half. What is the objective value of this?
should be 7.5.
Okay, and I have an objective of 7.5. And now, can this give us an important information? Okay, you understand? Follow my reasoning, please. In my wildest dream, if I can melt the gold, I can go home with an objective of 7.5. For the initial problem, can I dream of an objective of 8? Even if I could melt the gold, I still cannot gain 8. Even if I could melt the gold, I cannot gain weight.
Running is the maximum.
This means that I cannot go home with 8, with an objective value of 8. This proves us that the optimum value for the original problem is 7. Because as long as this problem is stated, let's say officially, in integer variables, the objective value, it will be an integer value. I know an integer value of objective of 7. What did I compute previously? Even if I would replace z by r, I'm at 7.5. This proves that the solution of value 7 is optimal in integer values. And the story is finished. This is called in computer science and optimization the linear relaxation. This is the linear relaxation of the problem, which is easy to solve because you realize even at this, you understand me, even at this very small scale for a computer, a problem with two variables is very small, but a human scale, you realize that even this problem is more easy for you in real numbers than in integer numbers. Okay, this is the...
You cannot take 7.5.
No, because
It's in Z.
the 7.5 is the value that I could obtain in my wildest dreams if I could melt the gold. It's a relaxation. We relax the integrality of the variables. We allow them to be fractionals, okay? I have more freedom of choice than in real life. I don't know if I make myself clear. No?
No. Z domain Z.
Z means integer,
Integer, not
not real.
not.
Z is integer. Okay. Okay. Now I move to the programming part if you want. I will stop at slide 7 if you want. This is 9. This is 7. Slide 7 will tell you how you could write this problem in a solver called GLPK, but this is not required of you because we work with Julia. This is the code of the problem to solve this problem in Julia. So if the guy had access to a computer, he could write a program in the following Julia program. You start like this, using jump, using GLPK. Jump, it's a library of Julia. I think Safia Kedat told you about it a bit. It's in the document. If your colleague told me just when we started the session, you were not all here. He told me a PDF where there are some installation guidelines, and one of the points consists of installing this library. Okay, then, but this is the same library for all Julia programs in optimization. This library, for instance, pay attention, is not a library. This is an external solver. So understand this. In Julia you write a model. For instance, you'll see it right away. This is the objective file, a function, 3x plus y. This is the solver. This is installed separately. This is the thing that will help you solve the problem. The solver, you understand it? So you write the model in Julia. This is the model of the problem. And when you ask to optimize, it will call an external solver. You can use either GLPK or CVS. I don't care. Use one of the solvers like this. This is how you declare the variables. This is the model, which is generated this way. M. This is variable X for the gold. And you can add this to tell him that this variable is integer. Okay? You follow me, please, because you'll need this in the computer class. If you don't put this, it will consider the variable is real. You can put it or not. If the variable is real, you don't put it. If it's integer, you put it. Okay? Variable y. Now the objective. You use this arrobas around to get the objective, the variables. You put the model each time. M is the model. You maximize the objective. 3x plus y. Okay? You remember golden bills. Any question? Then define the constraint. Constraint model 8x plus 3y. You remember? These are the kilograms and this is the volume. Okay? Then we continue to the next slide and I will stop here if you want
A question from the
Sorry?
question from the slide. This one. In the configuration we use the CBC.
Okay.
So if you want to use this one, we should download it.
It's separated. But use CBC. Instead of GLPK, you write using CBC. Instead of GLPK dot optimizer, you write CBS optimizer. I will write it with you if you want. Let me. I will write this with you. Okay, so why using like this? Using. Okay, you follow me? Using CBS. M is model CBC optimizer like this. Okay, capital O, and then variables with under x, tag, integer. Second variable y, integer. That's it. Okay. Tag, everything is fine. Now objective M, sorry, did I say M here, you follow me? M, you always say to give M to each. M is the model, okay, M like this. Sorry, you will have access to this slide. You can I will give you the slides right away, or I can give you let you take a photo of these two slides. It's all you need. All you need for the computer class is this slide and the next one. Tac. Objective max 3x plus y. Constraint M. What do I have? 3x. No, the constraint was 8 kilograms plus something like this. 3y is then equal to 20. And the constraint, tell me, like this. And the second one was 6 and 32. Any question?
I think the constraint one is 6y.
The second one or the first one?
The first one.
8, 3, 20.
No.
The second one is 6 plus.
Yes, it's weight 20. Okay. Then once the model M is defined, you have the constraints and the objective. Now we start optimizing and printing the solution. Optimize like this. Don't ask me why we need to put the exclamation. Just do it. And then objective you will make a photo of this program if you want. Objective value M. Okay, so this is our program. I will write it like this. And now I will execute to Julia. Okay, and it's quite slow because it's Julia. Sometimes it's slow for some kind of things, and there may be errors in my program. I'm not a robot. I can make errors. Okay, you see, I wrote it these kind of things will always happen. Pedagogically speaking, it's interesting to notice these kind of things because there is no problem if you have some errors. Errors are ubiquitous in computer science, but you need to know to solve them. So pay attention on the output reported. Slide 9, this is the name of the file. Line 3. Okay. Optimizer not defined. Line 3. Yes. Line 3 is here. Optimizer. And now I execute again, Julia. Sorry, it's not very speedy when I execute it like this. This is the output of Julia. He tells you the objective value himself. The time or other information, you don't care. The only value that you that was printed by me, if you want, is this small 7, which is the objective value. You understand me? Here, I can write a text, okay, and it will be clear. This is my output. You understand what I will write it like this. I will do it like this. Okay, so from here on is the output of my code. Please pardon Julia for, please excuse her. She is not so fast when I execute it like this, but generally speaking, if you execute it in a different computing environment, it can be very, very fast. Okay? Actually, the time, no, pay attention, the time, it's a bit complex. This is the time needed only to solve the problem in the solver. Not the total time, but Julia, it's a language with multiple software layers, and it takes a lot of time not to solve the problem. This is not what it takes time, but it compiles the code. It's a compilation stage that takes a lot of time, okay? Okay, and if you want to write exactly like in the slide, if you want to get the value of different variables, you can write something like, I will just say value dot x, okay, this is the value of x, and this is the value of y, okay, this is gold, you can write like this, bills, and I execute again. Okay, 2 gold, 1 bill. This is Julia. Any question? I don't know, how do you find this kind of code? It's okay. It's okay. It's one of the latest and the most modern languages for optimization, and it was designed to be as simple as possible to start with. There are much more complex languages over there in optimization. Any questions?
Yes, can you come again for the optimize function?
Here?
Yes. Do we need a space between the explanation?
No, don't put the space. Don't put any space. No, like this. Okay, and let me not put the stuff, the exclamation.
Sir, can you show us the code?
Of course. No, you need the exclamation, so you need to put it. Okay, so if you want, we still have only 1 hour now. Yes, we finish in 1 hour, and if you want, you can take a photo of this code, and this is basically all you need to start the computer class. Is all you need for today, because we only have 1 hour. Any question, any remark before finishing? No? Did you all install Julia? It's okay for everybody? And then I will give you the computer class on, it's printed on paper. And I think it's okay for 1 hour. Maybe the subject was written for 1 hour and a half. I thought I would stop at the half point of the session. But maybe you'll not be able to finish everything in 1 hour. I don't know, because it was supposed to be done in 1 hour and a half, okay? Or even more, but that's it.